And welcome back. This is part 2 of problem P5-15. That's a weird way to write a 5. 15. Yeah. All right. And we have just decided that we are going to need to know the magnetic field in order to find the magnetic flux, in order to figure out the flux linkage to find the inductance. And in order to do that, we're going to use Ampere's law to find the magnetic field inside the toroid. And our contour of integration is going to be as shown here. So we're looking at the cross-sectional view of this toroid cut like a bagel. And our contour of integration is going to be given by this red dotted line. And it's going to happen at some radius that we're going to call r. But luckily, the way that I've been drawing these pictures is not exactly the way that they've described it to us. Because remember, b is much less than r naught. So it looks a lot more like this in the side view, or like this in the bagel view. And in that case, what we can do is assume that the magnetic field is constant over the cross-sectional area. And because we can do that, all we have to do is find the magnetic flux density, B, at R naught, and then multiply by the cross-sectional area. So how do we do that? We do it with math. So I'm still going to write down this contour integral of B dot dl is equal to the total current passing through the cross-sectional area defined by that contour. That's total current. In fact, I'm going to denote this I sub t so you don't get confused and think this is just the current carried by the wire. What is that total current? Well, we're told that we have n turns, so I sub t is equal to n times I, the current on the wire. In which case, our Ampere's law integral then becomes contour integral of B dot dl is equal to mu naught n I. But we were just saying that the magnetic field is going to be constant over the cross-sectional area, so it's the same anywhere within the toroid. It's constant over the cross-sectional area. Because of the direction that the wires are wrapped, we're going to know also that B is phi directed. So then when I actually evaluate that integral, it's going to be integral from 0 to 2 pi of some constant value of b, which I'm going to call b naught, times a hat phi. And that's going to be dotted with my expression for dl, which is a hat phi r naught d phi. That's dl. And that again is equal to mu naught n I. So that dot product of a sub phis is just going to be equal to 1. This factor of b naught can go out to the front of the integral. And then when I write that down one more time, I have B naught in B naught. This really hates the way I write the letter B. Integral from 0 to 2 pi. Oh, and R naught can come out to the front too, because that doesn't depend on phi. So that's just an integral of d phi now is equal to mu naught n I. And when I evaluate that, I have 2 pi R naught times B naught is equal to mu naught n I. So then B, which is equal to B naught A hat phi, is going to be equal to, once I solve for B naught, A hat phi times mu naught n I divided by 2 pi R naught. Not bad. So now we found the magnetic field by applying Ampere's law. The next thing that we're going to need is we're going to need to find the magnetic flux through a cross-sectional area. So let's set up the geometry for that. For this one, imagine the cut in half the short way cross section. We're looking at the toroid cut in half like you're sharing the donut with your friend now. And in order to find the surface that we're going to use for finding the magnetic flux is going to be the cross-sectional area of the toroid. Find flux through here. So, and then once we have found the flux through that surface, we can find the flux linkage, that's capital lambda, which is equal to n times the flux. And again, this flux is equal to the integral over the cross-sectional area of B dot ds. Now, this is the thing. Since little b, the radius of the cross-sectional area, is much less than r naught, the mean radius of the toroid, we can assume constant magnetic flux density, B, over the cross-section. In that case, the flux is approximately equal to B naught times pi b squared, because B naught is phi directed and ds is also going to be phi directed. So if I substitute in my value for B naught that I have there, I have mu naught I n over 2 pi r naught times pi b squared. And those pi's cancel out, and then I have mu naught I n b squared over 2 r naught. And that's, I'm sorry. Yeah, that's fine. That's for the flux. Now, that's the flux through one winding. We have n windings. So the total flux linkage is going to be equal to, well, approximately, because remember I'm making an approximation for the magnetic field value, is going to be N times the flux. Really, that's a definitely equals, but I have an approximate value for the flux that I'm going to use. So that, if I add that extra factor of N, I end up with mu naught I N squared B squared over 2 R naught. Lastly, I'm going to apply the definition that we have for the inductance, L, which is the total flux linkage divided by the current. And subbing that in, I have mu naught N squared B squared over 2 R naught. And we're done. So that was the end of the original problem, but I want to go one step further, and that is how much stored magnetic energy do we have here? There's two equations that we can use for this, and we're going to evaluate both of them and find that they are equal to each other, so that's great. First of all, the stored magnetic energy in an inductor is going to be, Wm is the stored magnetic energy, is going to be I squared L over 2, which in this case is going to make it mu naught I squared N squared B squared over 4 R naught. Easy enough. We already had everything in there, so it was just a question of substituting. If we don't have an inductor in particular and we just want to find the stored magnetic energy in some sort of magnetic field, then we can use Wm, the stored magnetic energy, is equal to 1/2 integral over the volume B squared over mu dV. Or if you have B and H, that's equivalent to writing 1/2 integral over the volume H dot B dV. In very few cases, but they do exist, H and B might not be in the same direction, and then you use the right-hand one. So, since we have B is constant over the cross-sectional area, and in fact everywhere within the toroid, and it's 0 outside, we don't actually have to do that integral, because we can just do B squared over mu, and in this case, in our material, this is mu naught, because our material is air, times cross-sectional area times 2 pi R naught, and that'll do it. If we didn't have this situation of the constant magnetic field, we would have to evaluate the volume integral, and we would get a similar value, but not exactly the same. But again, not generally okay, because we usually have to do an integral. All right, but since in this case B does not vary, then we have, oh, I'm sorry, and that should have a 1/2 in the front. I dropped my 1/2. In that case, we have 1/2, 1 over mu naught, this whole quantity squared, mu n I over, that's a mu naught, 2 R naught, sorry, that's a 2 pi R naught. That was our original equation for B. And then we're going to square this whole thing. Then we're going to multiply it by the cross-sectional area, pi b squared. Then we're going to multiply it by 2 pi r naught. And then a whole bunch of things are going to cancel out. So this 1 over mu naught is going to go away because we've got some mu naught, we've got a mu naught squared inside these parentheses. We've got one of these factors of 2 pi r naught is going to go away because of that multiplying by the circumference of the toroid. Another factor of pi is going to go away because of this pi b squared here. And in the end, what we are going to end up with is mu naught n squared I squared b squared divided by 4 r naught, which if I have done, that's equal to Wm. If I've done my math right, that should be the same as what we had up here, and it is. So there we go, 2 ways to find stored energy. And that's the end of part 2.